In this video, we're going to be discussing the idea of a probability distribution function, sometimes known as a PDF. And we're specifically looking at what we call discrete random variables. So a couple of things about those. Let's start with what is this idea of a PDF, so a PDF function. Probability distribution function is one in which it demonstrates all the possible probability values for a particular variable. So in other words, every outcome is listed and each one of those outcomes is given a probability. So a couple of characteristics that are requirements to be a probability distribution function. First one is the probability for each outcome must be between 0 and 1 inclusive. So the probability can be 0. We would write it like this. Oh yeah, and it also can be 1, and it can be any number in between. So we must make sure that all probabilities listed are listed in this way. They have to be either a decimal value, fraction value, or 0 or 1. And then the sum of all the probabilities must total to 1. The reason for that is that what we're looking at in a probability distribution function is we're representing every possible outcome. So that means the total of all the probabilities would be representing 1 or 100% of the outcomes. What we're looking at in these probability distribution functions are variables that we would call random variables. So the idea of a random variable is that it is the value that we can't predict what is going to happen in an experiment. It could be things as easy as rolling a die or drawing a card from a deck of cards. We don't know what we're going to get when we do those events. It could also be things like whether or not you get a speeding ticket today. There's a lot of different random variables. We don't know the outcome of the day. And then discrete random variables are more specific types of variables. Those, remember, discrete means we can count the values. And so these are going to be countable variables, like you might count the number of times a 6 appears when you roll a die, or you might be able to count the number of speeding tickets a person gets, these kind of things. So what we're going to do is we're just going to look at some examples here and work our way through some. So I'm going to pull up some examples next and see if I can make that happen. Okay, in this example, first, we want to look at the probability table that's given. Typically, these PDF or probability distributions are drawn in a table. And notice the capital letter X is given as this is our random variable that represents something. And then P of X. Maybe this is the amount of money a person wins from the lottery. And if they lose money. So that could be that. And these are the probability values for each. You'll notice there's a missing value. So in order for us to complete the table, we think about what are the two requirements to be a probability distribution. First, probabilities must be between 0 and 1. So we can see so far all of those are values that are between 0 and 1, and we need to find the missing one. Also, we know the total probability has to be equal to 1. And so because of that, we can add all the existing probabilities together. And if we total them up in this problem, when you add those together, you'll see that each of these adds together and it adds up to a total so far of 0.9. And so, or 90% is covered. So what's left? 1 minus 0.9 would be the missing item in here, or 0.1. So we have a probability for -8 of 0.1. In the second example, it says, is this a probability distribution? So in order to do that, again, we think about our requirements and we have to check. First of all these are values between 0 and 1. So we don't have any kind of strange things like a negative value or something like greater than 1. So that part is met. And then secondly, we are going to find the total. So if we total those probabilities by adding 0.3 plus 0.3 plus 0.15 plus 0.2, you'll find the total of this to be 0.95. So does this, as written, represent a probability distribution? We would have to conclude that no, it's not a distribution. It's not a PDF as we described, because it doesn't include an outcome. There's something missing here. There's the other 0.05 that hasn't been represented. So a true probability distribution must add up to 1. So let's take a look at another example. And we'll scroll the page here a little bit. In this example, we're going to complete the probability distribution table. And in this example, X represents the amount of money won or lost by a player in a game of chance. So this could be any kind of game of chance. It could even just be the lottery. And so in this example, P of X represents the probability of each outcome. So there's 3 possible events that could happen in this particular game. In this particular game, a player could win $4. They could break even, so they win $0, or they could lose $6. And each of the provided probabilities have, corresponding probabilities have been given to us. And so let's go ahead and we're going to fill in this probability table using the information that we have, so that we have the complete outcome list. And so remember that the probability distribution function shows all possible outcomes. So let's start with an outcome of $4. You could win 4, that amount that you win. And there's a 23% chance, but we're going to always list these probabilities as decimals. So 23% shift the decimal back 2 places. We have 0.23. And then they could break even, which is a 0 outcome, which is 0.49. And they could also lose $6. So that's a negative outcome of 6. And the probability of that is 0.28. If you check the total here, the total of all these outcomes is equal to 1. So 100% of all possible outcomes in this game have been represented. The other thing to notice about our variable X is that all the values we list in this probability distribution are numerical values for X. You wouldn't have things like win, lose, or break even. You would have to put a number value to it. So they're numbers in these tables. In the last example that we're going to look at here, so we're coming along. In our last example, we've got a situation in this probability distribution function that's been given where X represents the number of speeding tickets a person received in 3 years. So as you can see, there's about a 38% chance that they got no speeding tickets. And all the way, every possibility is listed. So they could have gotten 0, 1, 2, 3, 4, 5, or 6 or more. And good thing, there's about a 0% chance of them getting 6 or more in that 3-year period. So good for them. So the probabilities are listed for each one. If you stop and total these, you will see it comes out to 1. So it is a true probability distribution. What we're going to do is answer a few questions about this distribution by thinking about what is it telling us about different scenarios. So let's start with this scenario where we have, what's the probability that a randomly selected person has received 5 tickets? And notice in the statement it says probability that X equals 5. So that means exactly 5 tickets. We can go to the table where it says 5 under X, and the probability is 0.0123. So we can read the probabilities directly from the table. Another thing, question that we have, and I think I'll shrink this a bit so we can continue to see the values at the top. Let's look at part B. In part B, we're asked, what's the probability of them receiving 3 tickets in a 3-year period? So that means X is equal to 3. So that value would be 0.1501, a probability of about 15%. For the next couple of examples, what we're going to be doing is considering the probability of multiple events happening together. from this same scenario of speeding tickets. So let's read part C together here. Part C, what is the probability that a randomly selected person has received more than 2 tickets in that time period? More than 2. So you want to be careful. And remember, we're trying to use good logical sense. More than 2 means 3 or 4 or 5 or 6 plus. So any of these outcomes are included in more than 2. 2 is not part of the group. And so when we think of the word or in probability, we think addition. So none of these can happen at the same time. So we don't have to worry about the possibility of that. So we can simply add together these independent events. So we have the total is going to be 0.1501 added to 0.0413 added to 0.0123, and we'll write it, but not worry about it, 0.0000. So each of these numbers are the particular probability for 3, 4, 5, or 6 plus speeding tickets. When you total all that up, it turns out that there is, for this probability, a total of 0.2037. So that means in that 3-year period, there's about a 20% chance that the person would get more than 2 speeding tickets, which isn't a huge amount. Okay, and then let's look at part D to finish it off. What's the probability that a randomly selected person has received 3 or less? That's a little more desirable than 2 or more. So 3 or less. So notice the wording is a little different. 3 or less. So that means it could be 0 or 1 or 2 or 3. 3 is included because of how the statement has been worded. And so for this, because of that fact, and these are all independent events, we're going to add the probabilities together for that. We want 0 or 1 or 2 or 3. And so when we do that, it's 0.3767 plus 0.2374 plus 0.1822 plus 3, which is 0.1501. When you add those 4 together, you get a probability of 0.9464. This is the probability of getting 3 or less speeding tickets. So that's about a 95% chance, which is a lot better, I guess, of getting less speeding tickets. And so this is to get you started working toward module 4 assignments.